Okay, it looks like we're just about set up. We're going to wait out that final minute as usual, but welcome back from the holiday, everyone. Hope it was restful for you and not too busy. And it's official. We're now in week 2. Welcome back, everyone. It's always kind of a weird start when we have a holiday like the one we had here. We're trying to get into kind of a groove of how the class is going to work so we can get into a normal pattern of how this course fits into your schedule, how it fits in with your other classes, home life, work life, and that kind of stuff. So it's nice to have a holiday, but it just means we'll get back into the groove of a normal week by week session in week 3 already. But our plan so far for the day is finish off the section 5.1 notes. We just have 3 more examples, and then we'll move into section 5.2, where we're going to define the sine and cosine functions. But any questions at all, folks, before we get started today? Okay, one other announcement I want to put out there as well is this class was kind of challenging to get off the ground, mostly because it's a fully online class, which included lots of interesting out-of-state kind of setups that we had to do for the in-person examinations. I've been doing quite a lot of research between last Friday and today, and I think I have a great canvas nailed down for just about every single person in this class, except for one state. Rhode Island seems to be kind of a tricky state. I'm still working with that student to get all the details hammered out and where that testing is going to be located at. And so I'm proposing to the class something I don't typically do. I'm thinking just because of the timing, it took a while to get the course off the ground with all the things that we did on week 1, and also all the extra work of getting the testing centers in line. I'm proposing we're moving exam 1 over to next Monday so that we all have a little bit better breathing room. No one's feeling a little too stressed, wondering about the details when we're already in week 3 here. How's that sound to folks? Does anyone have any objections or additional comments about that?
Um, so that would be Monday the 21st,
Yeah, that's
sorry,
right. So the 22nd
or the
through
22nd.
26th would be the exam week. Exactly.
Um, I won't be in the state of Utah that week.
Oh, I see. That could be a bit of a challenge. I'll have to think about that. So it seems like we have lots of people feeling okay about it, but I definitely don't want to upend anyone's schedule as well. So I'll have to think about that. It's kind of tough moving exams because of those kind of challenges. Everyone's planned around it, as well as the fact that we did say in the syllabus itself, those are the one things that we like to keep firm. I think we said we will keep them firm. So I'll work with everyone directly on making sure the exam stays where it is, just so that not too many people's schedules are going to be upended. Thanks for reach or speaking about that one weird challenge about the schedule and being out of Utah on that day. So for any additional issues I might have on getting people set up with their testing centers in the various states, particularly Rhode Island seems to be the tricky one. Probably what I'll do is make a special arrangement if we're running a little behind on the setup so that the couple students that might be affected, I might send their exam to the next week. Does that sound right to folks? Sorry for teasing moving an exam date, but then resolving it to keeping it where it is.
No, no, it's all good. I appreciate that. I was just like, oh no, my entire vacation
Yeah,
that I've had planned for months, I am now in trouble.
yeah, I understand. And that's why I like to make an announcement, throw it out to the whole class, because who knows who else this could totally just destroy their schedules as well. Definitely don't want to mess up anyone's vacation, for an example. So what we'll do is we'll officially keep this exam one date firm. And if I do run into any 1 or 2 particular students where I just need to do a little bit extra work to get testing centers lined up, we'll move those particular exams. So, by the way, that means when I get to the weekend here, closing out this week, I'm going to make the content on exam one firm. It'll just be extra information over these sections and so on. It's likely going to be sections 5.1, 5.2, and 5.3. So the sections on defining and working with trigonometric functions. And I'll also be posting extra exam materials as well as working with everyone on how to work with the testing center that you've been assigned to and that kind of stuff. Well, that's our full set of announcements for the day. Any questions or comments at all, folks, with anything going on at the moment? Okay, let's get started then. We're just about done with section 5.1. Oh, sorry, Luke, I saw that you raised your hand just now. Question, Luke?
Yes, can you hear me okay?
Yep, you're coming through great.
Okay, cool. So my internet kind of cut out briefly right as you were explaining what the plan was, and so my audio just completely muted. So my understanding that we're pushing the first exam out 1 week.
We actually had some conflicts with moving it out 1 week. So what we're going to do, again, sorry for raising that offer and then taking it away, but it looks like there is some conflict in the class with keeping it on this date. So, or moving this date down. So we're going to
Okay.
keep it firm on this date right here. It'll be just over 3 sections, so it's not going to be a big exam. And with anyone that has any particular issues with getting the testing center worked out, any of the details sorted out, particularly if you're out of state, I'll work with you directly, and if we have to, we will move that exam to the next week. So officially, it'll be on this week here for Monday, September 15th.
Okay. Thank you.
Yep, absolutely. Any other questions so far? Okay, let's dive in. Here's where we left off in section 5.1. I took a quick screenshot of the format that we needed on working on these problems. And just a kind of a quick rundown. The major idea with example 4 and 5 is just converting between radian measure and degree measure and getting a feel for how to plot these angles in standard form. The circle is optional, but the circle is going to be a big problem, big part of trigonometry. So we're bringing it in as we do these sketches. So we plotted negative pi over 6 or negative 30 degrees to be here in quadrant 4. It went clockwise because of the negative angle. Pi over 4, the 45-degree measurement, is here in quadrant 1. It's in quadrant 1 because if it's a positive angle, we rotate in the counterclockwise direction. And 270 degrees ended up on this axis here. Or it could be thought of as 3 pi over 2. So all we're doing is running through a couple more on these problems on these notes to finish out this section. Next one to try out is negative 330 degrees. We're converting this to radian measure. So we use this factor, this factor right here. We'll multiply by pi, divide by 180 degrees. First thing we might do though is, just like we did in the other class after the really long weekend, is maybe just plot this whole thing. Because of the negative direction on this one, we're now going in the clockwise direction. So if you rotate this far, that's negative 90 degrees. This far is negative 180 degrees. And this far is negative 270 degrees. Notice it's just on the opposite end compared to that 270. So if we rotate all the way down, I'll erase that in a moment, that would have been negative 360 degrees. So we just want to come a little bit shy to about to right here, 30 degrees short of a full rotation. So that's negative 330 degrees. So we plotted the angle. Here it is in standard position. Next thing we'll do is convert it to radian measure. Yeah, go ahead, Andrew.
So is there any particular reason we would call that like negative 130 instead of just positive 30? Or, I mean, they're the same. So is there a situation where we should just swap from one to the other?
Yeah, absolutely. Later on in the next sections, we're going to notice negative 330 degrees is just kind of a wonky angle to work with. It's the same as 30 degrees, absolutely. So if we're doing cosine negative 330, we will simplify it to say, well, 30 degrees is the same position, easier to visualize. So yes, we will oftentimes do exactly that. For the moment, it's all about just placing it on the unit circle or in standard position, just getting used to how to plotting them. And we'll start taking those tricks later on in sections 5.2 and 5.3. Other questions at the moment? Okay, now quick arithmetic on this one for the conversion factor. We're taking negative 330 degrees, multiplying it by pi over 180 degrees. When we convert that, we're going to get, let's do some quick arithmetic here. You could, if you like, divide by 10 degrees on both sides. That wipes out the 0 and the degree symbol. So now it's just negative 33 divided by 18. We can divide 3 here to get negative 11 pi. Divide by 3 here to get over 6. And so this angle at negative 330 degrees can also be thought of as negative 11 pi over 6. Or like the earlier question about this, you could call this positive pi over 6 as well, and that would have been totally fine. So there's infinitely different ways to visualize these angles that we are plotting. Oftentimes we're going to want the simplest form, but here is more of just following the instructions to the letter, see where things fall. So that's our quick rundown of doing these kind of conversions. Last two problems are just a couple fast applications that we can do while we're already here in this section. Let's take this screenshot along with this as we go. The next definition is kind of a nice one because, well, this is the next definition down below. Let me highlight it. This is a nice definition in the sense that it's just a reformulation of the formula up here for radian measure. Radian measure is a formula of 3 different variables. That means it could be formatted in 3 different ways, depending on the variable you decided to solve for. Here, we've solved for the arc measurement, S. So if we want to find the length of an arc of a circle in radius r, so here's a particular circle in radius r, and here's the arc length S, we just use this formula here. And the way we got that formula is we just went up to this one, multiplied both sides by r to clear the denominator, and this is what results. So it says, find the arc length of S in the diagram below, but we have to be really careful with this formula. That's why this is kind of an interesting one to do in class. One thing that it never really says outright, but is super important, is the angle is in radian measure. So that means we have a big problem right here. The very first thing we have to do is convert that angle itself out of degrees into radian measure before we even get started. So really this problem is all about how long is this length from here to here in a circle of 1 inches if the interior angle is 150 degrees. But it's 2 problems. We also need to convert 150 degrees into radian measurement. So same as the problems above, multiplied by pi over 180 degrees. Simplify, this portion cancels out. Now divide by 3, numerator, denominator, and we get 5 pi over 6. So we're all set now that 150 degrees can be rewritten as 5 pi over 6. And now the formula is going to work as normal. So here's us using the formula finally after the scratch work above. The arc length S is going to be, let's just copy the formula down first and then evaluate it. Radian measurement times theta. The radian measurement is the 5 pi over 6 that we found here. And I'm noticing my color coding does not actually go that way. Let me fix that. Or hang on. That was right. So R for radius is the 1 inches. I got that confused with radian measurement. That's not helpful. 1 inch multiplied by the angle theta in radian measurement. That's 5 pi over 6. And it just says find the arc length, not do anything else to it. So we give the exact answer. That's what we're expecting on this one. 5 pi over 6 inches. If you decide to give it a decimal approximation, that would be okay. But if the problem just asks for the arc length, the exact answer would be the main thing I'm expecting on this one. And really, you're just putting it in the calculator as a double check to see if it really makes sense on the diagram. We did it, folks. Now with the radian measurement formula above, we can just solve for S, find the arc length of a circle in this kind of way. Really, the only thing to worry about, like we mentioned, is the fact that we're using the radian measure. So if something is in degrees, I think this happens at least once in the homework, be sure to convert it and then you're on the right track. Any other questions with this one here, folks? Okay, one last really quick application. Oh, first question, Luke.
Yeah, I was just thinking, is it only in the case of a unit circle, or is uh the measurement in radians going to be the same as the arc length? Is that always the case, or just with the unit circle?
Well, by unit circle, you're meaning that 1 inch right here. But
Yeah.
yeah, this formula could be worked for any radius whatsoever, and it would work out just fine.
Well, so what I'm just saying is the arc length always going to be the same as the angle measurement?
No, not at all. Say if this was like 2 inches right here, we'd have put 2 inches here, and then there would have been a 5 pi over 3 for a difference there.
Oh, okay.
So yeah, this one's kind of a weird one, right? The actual angle itself came out as the arc length, but good observation. That's only because it was a unit circle. And that's the
Okay.
only time that could occur on these kind of problems.
Okay, thanks for the clarification.
Yeah, absolutely. Other questions so far? And good observation about that one. Okay, well, here it is, folks, the last problem of this section. These notes felt like they took a while to get through, but that's okay. The course was just starting out. We're getting used to the domain of the trigonometric functions, probably just as important as the functions themselves. And finally, here's the last problem of the day, another interesting application that just happens to be available to us. This isn't every single application section 5.1. So if you read the entire section, you might notice there's other things in here. Occasionally, this is how the notes are going to look. I'm going to try to take just the main ideas that will mostly show up on homework and on exams. And there could be other interesting things in there in the reading as well. Reading is still valuable because it's interesting to see how all these ideas connect. But this is the scope of what the homework will look like, and therefore the exams as well, up to a question like this one. So it's the sector area formula. What we mean is we have a big circle, really. This is kind of hard to draw because of where it is on the paper. Let me see if I can fix that. We have a big circle, really, but there's an internal measurement of 30 degrees in this circle of 5 inches. And we just wonder, what is the area of this pie slice if you're thinking of pepperoni pizza or something? Or more mathematically said, we want to know what is this area of this sector. So that's another really nice, interesting trick. But just like before, we have to worry about this part right here. The central angle has to be measured in radians specifically. So a problem like this being thrown at us already is a bit problematic. We can use this formula only if we're really, really careful of each of the components. Maintaining the same color coding, all we need is the radius on this one and the angle theta. Well, theta is 30 degrees. Anyone happen to recall what that would be in radian measurement? If we're not sure, the good news is it's really fast. Well, sorry, go ahead, Logan.
5 pi over 6.
Exactly. So if you did the conversion, 30 degrees times pi over 180, let's might as well put it on the paper. Then like Logan said, this is just pi over 6 radians. So now we have the radian measurements lined up. Thanks, Alex. Exactly, so pi over 6 here. That's kind of the major goal of these notes, just to get kind of familiar with what does this look like now in radian measurement. And finally, to simplify this problem, let's actually add a little bit slightly different instructions. So this is just a really quick edit. Find the area of the sector and round the area to 2 decimal places. I want to add that in just for sake of variety in instructions. Sometimes the homework asks us to specifically round, and let's do that ourselves here. So working the formula, area is 1/2. Radius squared times theta means for our problem, area is 1/2. We'll take 5 inches, square it, multiply by the angle theta, but ignore the degree measurement. I guess this is kind of a sell on radian measurement. A lot of the good formulas in trigonometry are going to be in radians to begin with. So that's a part of the reason we like practicing with this content. Then at this stage, it's just a matter of simplifying. We're going to put it in the calculator, but it's probably easier to put in the calculator as a simplified expression. So 5 by 5 is going to give us 25 times pi, across the denominator, 12 inches squared. I'm not picky about rounding, so if you did leave it like this on say, a homework problem, that's probably okay with me. I don't think I would take off points. But reasons you might want to round is if it says to do so in the instructions, you might be checking the back of the book to see how your answers compare with the odd answer solutions, and it would give you the decimal approximation. So let's do it ourselves. Let me grab a quick calculator. Forgot to load this up. I'm going to try to get in the habit of making sure this is available. The one I use often for classroom demonstrations is just going to be Desmos. Throw all that into the calculator minus the unit, 25 pi 12ths, and I think I said 2 decimal places, double checking. That'd be 6.55 inches squared. And we did it, folks. That's our next trick on the end of this section. Now you can find, for any size pizza, you can wow people at a party if you get a good angle measurement in radians on the exact area of that pizza slice. So cool new trick. Any last questions at all, folks, on the end of this example? Okay, let's maybe add just one additional thing to this notes. One thing that gets really important, especially as we're getting into section 5.3, is knowing where certain key angles are going to end up. So let's do just a quick sketch to practice this. Key angles that we are really interested in. On the Moodle website, you can take a look at this under common angles and radians. Let's open this just to take a quicker visual. This is something you might want to have at the ready just as a quick reference. But word of warning, these are some angles that we do have to have memorized, these positions, working in trigonometry. So the more you do the practice work that we're going to do on the notes, the easier it is to get through the trigonometry. I'll give some notes on what goes on in quadrant 1 for these angles, but we're responsible of knowing how the rest of the angles are going to work throughout the entire unit circle. So we'll practice it as we go along through the notes and homework exercises. So here are these key angles. And again, this is a good exercise to do on your own. Just take out a clean sheet of paper, draw a circle. Let me try again on the circle. We're trying to make this one look nice. Good idea to put just the XY plane on it. We'll need those axes anyways. And the way we start this out is do the multiples of pi over 6 and plot them as we go. Well, the first multiple of pi over 6 is really 0 times pi over 6 for 0. So it seems kind of weird, but yeah, 0 is right here. That's going to be an important angle. No rotation. 0 is 0 in radian measurement, and it ends up right here. Then it's 1 times pi over 6 for pi over 6, where you're doing a 30-degree rotation. And we'll visualize it like this. This is freehand, so not perfect, but just do the best you can. Next is 2 times pi over 6, and this is where trigonometry gets a little bit interesting. It would be, in a certain sense, convenient if we called the 60-degree rotation 2 pi over 6. But everyone wants to simplify things in mathematics, so it's almost like 99.999% guaranteed. This one's put down as a pi over 3. But it's still important to know that's just the second multiple of pi over 6. And now at this point, you kind of see the name of the game. The multiples of pi over 6 happen to be key angles that we're going to use repeatedly throughout the entire semester. And it's very helpful to have that as a picture in your mind, precisely where they are. But first, 3 pi over 6 reduces to pi over 2. Let me put this one in a different color for reasons we'll see later. 4 pi over 6. Fourth multiple reduces to 2 pi over 3. So here's 2 pi over 3. 5 pi over 6 does not reduce. That's kind of nice in a way. And 5 pi over 6 goes way out here. That's supposed to be a 6. Let's make that apparent. We rotate down to the next one. That's 180 degrees. But that's just 6 pi over 6, which reduces to pi itself. The next one, 7 pi over 6, which doesn't reduce. Eight pi over 6 reduces to 4 pi over 3. You might be noticing some interesting patterns already. 9 pi over 6. This one reduces to 3 pi over 2. Let's put that one in black as well. And I'm kind of running out of vertical space. Let me see if I can scroll ever so carefully. There we go. We've got some more. 10 pi over 6 also reduces to 5 pi over 3. So that's 30 degrees off this y-axis down below. Finally, 11 pi over 6. This one doesn't reduce. Have to like the prime numbers like 11, 5, 7, and so on. This one ends out here. If we kept going, I ran out of space, but let's see if I can just put it over here to the side. We would have gotten 12 pi over 6, but that just reduces to 2 pi. So the starting location, like a comment we were talking about earlier, there's millions of ways, better said, infinitely many ways to represent this particular terminal point. It's either 0, 2 pi, 4 pi, or so on. So on the right-hand side, we either have 0 or even multiples of pi. Left-hand side, we have pi or 3 pi, 5 pi, and so on, all the odd multiples of pi. Doesn't hurt to write that in, just for emphasis. Way up here on the y-axis, we have pi over 2. Down below is 3 pi over 2. Kind of interesting that those have divisions by 2, but it's just a consequence of how the multiples are reduced. Another thing that's interesting is how the pi over 3's get represented. I'll make this a temporary color because I don't want this to get too busy. But notice if you're just 30 degrees away from the y-axis, your denominator is always divided by 3. So 1 pi over 3, 5 pi over, hang on, that looks like a typo, right? That would have been 5 pi over 3. Looks like I was trying to copy this and I put in 5 pi over 6. So watch that correction right there. Let me make this a little bit more apparent. If you copy this down fast like I did, it was a 6. It should be a 3 on that one. This diagram doesn't do any good unless the values are right. So we have pi over 3, 5 pi over 3, odd values on the left or on the right-hand side. On the left-hand side is 2 pi over 3 and 4 pi over 3. And these are all the multiples of pi over 6. Well, not all of them, but it gets a little too busy to put every single one. There's infinitely many. These are a lot of key angles, but it feels like there's some gaps like here. That's the other set of angles we want to put in. And here is the first one. All the pi over 4's. My chart's getting a little busy, so I'm not going to write down all the multiples. but it's the same kind of idea. This is rotation by 45 degrees, or pi over 4. Over here, if we rotate all the way up to here, this is 90 degrees, or it would have been 2 pi over 4. But notice 2 pi over 4 does in fact reduce to pi over 2, so that's just a different way of saying the same position there. So here's pi over 4, 2 pi over 4 reducing to pi over 2. 3 pi over 4 is right here, if I can get the mouse to not travel like that. 4 pi over 4 is here, but 4 pi over 4 does reduce to pi. So we just leave it as it stands. 5 pi over 4 is way down here now. Then finally, 6 pi over 4. 6 pi over 4 reduces to 3 pi over 2, so we don't need to put anything different. We usually leave it as 3 pi over 2 reduced. Next is 7 pi over 4. And this is the whole chart of the main angles that we're going to be studying extensively. We want to know sine, cosine value outputs in section 5.2, and then the next section, the rest of the trigonometric functions. Well, this is something good to practice. It's not a bad idea to have this available occasionally as well. If you go to the next table down below, it's the same way to represent the same information. But curiously, it gives us coordinates to various ordered pairs along the unit circle as well. That's what section 5.2 is going to be all about. Well, that was my last comment to make on this section 5.1 notes. Any last questions or comments at all, folks, with the conclusions here? Okay, well, we did it. Section 5.1 is completed. That means it took us a while to get there, kind of a slow start of the course. Sorry about that. Feels like we're going fast, but sometimes it's just not quite fast enough to keep up with the syllabus. But our section 5.1 is now done, so that due date here is now considered official. We're going to start section 5.2, complete it when we return on Monday of next week. And it is a shorter section, so every sections are going to take so long. Sorry, my computer just yelled at me. Here's what section 5.2 looks like. So finally, we're going to define the sine and cosine functions, and we'll do it through the unit circle diagram. Unit circles come up a couple times already. Let's draw it out and say what we mean exactly by this. So the unit circle, well, it's definitely a circle, so there it is. It's implied when we say unit circle, even though that's an implicit implication, that the center is right here, the origin of the XY plane. And then finally, the unit circle is just x squared plus y squared equals 1, the equation of a circle with radius 1. So this is an interesting way to define functions if you think of how it was done in college algebra, defining polynomial functions or logarithmic functions and so on. This is a lot different. We're starting with an algebraic structure from this equation here, the unit circle itself. And now we take an angle measured in standard position. In this section, our author decided to use t instead of theta, so I copied it in on our notes. Standard position means we start at the positive x-axis, and if t is positive, we're rotating counterclockwise. This could terminate in any quadrant, but for the sake of my diagram, I'm going to let it terminate right here in quadrant 1. Looks like a 45-degree angle, but that's just coincidence. Let's maybe make it seem a little bit off, harder to tell. So here's angle T, measured in the standard position. Next thing we take is a point, XY. Color coding is kind of helpful already at this point. It's indicated as a P, then the coordinates XY, but I'll just write it in this way. Just XY without the uppercase P to say point. So once we have those coordinates, this is our fundamental definition for the first 2 trigonometric functions. The remaining 4 we'll discuss in section 5.3. it's just going to be based off of these two. So this is like the fundamental definition in trigonometry. What we'll say is cosine of the angle t in radian measurement, notice that we're using function notation here, is the output x. I think on the original notes, I noticed it this morning. This was written as just a sine t without the parentheses you often expect with function notation. But that's okay because you can just say sine t without parentheses, much like you might have written natural log 5 in an algebra course without parentheses. Putting in parentheses is usually my preference. It's an honest to goodness function if you say sine. So I'd like to emphasize that personally with parentheses, but it's not mandatory. Occasionally I will drop those parentheses if it just makes sense. So sine of the angle measurement t is just simply the second coordinate y. That's a pretty interesting way to define functions. And just with this algebraic structure already, we can start evaluating some trigonometric functions right away. Others might be a little bit more challenging because, well, we'd have to say, how do you evaluate at 2 pi over 3 versus 4 pi over 3 and so on? That's part of the purpose of measure or memorizing where all these angles land. Well, any questions with the definition, folks, before we give example 1 a try? Okay, so it says, evaluate the following. Looks like we have quite a few evaluations to get through, but if all of it's based on the unit circle, this is not a bad place to get started. In fact, for many of the trigonometric evaluations we'll do in this class, you'll notice that this is the first thing I write down. If you're really good at this, you might be going into your mind's eye, seeing where the angles land and going from there. But I think a lot of people can really benefit from just drawing this out as a sketch. If it says cosine pi, pi is playing the role of this angle t, and from our last diagram we put down, we know pi ends up right here. What we then need are the coordinates of this point. But the hint is that each time I draw a circle, even if I don't write out x squared plus y squared is 1, we're assuming it's a unit circle by default. So that's our implicit assumption in this class. That means the radius is 1, so the distance here to that dot is 1, and that gives us coordinates. This is right at the point -1, 0. That also gives us the pretty much entire answer on this one. Cosine at pi is always going to be the first coordinate at the terminal position of rotation pi. So this evaluates to -1. Likewise, sine at pi is just the second coordinate right at this point where pi terminated. So sine at pi is 0. It's kind of satisfying as a way. Those are our first bona fide trigonometric evaluations. So congratulations, folks, who are getting through the notes. Any questions with that first evaluation? Okay, well, that was so fun. We'll have to try it again. So here's the next run through. Let's use the same diagram again with the new angle. Now it's at pi over 2. That's the 90-degree rotation, which ends up right here, the top part of the y-axis. All we need are coordinates. But first coordinate is 0. Second coordinate is automatically 1. Because the radius is 1, that's the distance here up to the top vertically. That means our job is done. We just need to keep straight in our mind which coordinate goes to which. Cosine, notice the direction here has been kind of mixed up, slightly painful. That's just to make sure we're keeping this really strict. Cosine in our mind should always say, go to the first coordinate. Cosine at pi over 2 is then 0. Likewise, sine at pi over 2 is 1. Once we get far into this course, maybe around midterms, this is going to feel automatic, kind of like saying 10 divided by 2 is 5. This is just the basic kind of almost like arithmetic of trig functions that we need to internalize so the rest of the course doesn't feel so burdensome. Better we get at doing this kind of work here, the easier the rest of the course starts to get. Let's hide the Pythagorean identity for now. And let's try this out again. Next angle is 0. That one's kind of weird, but recall 0 is just this right here. This is where the initial position, positive x-axis, just completely overlaps with the terminal position for no rotation. That's our 0 in radian measurement. We just pull coordinates just like before. Coordinates of this position go 1, 0. Trying to do color coding on this. Let me try again there. That means we have the full information. Cosine is the first coordinate. So cosine at 0 is 1. Sine is the second coordinate. So so sine at 0 is 0. Does that make sense to folks so far on doing these? Yeah, go ahead, Andrew.
I guess I don't really understand where you're pulling the coordinates from again. How did
Oh,
you know,
gotcha.
for instance, that the first one was -1, 0?
This one out here. Yeah, it came from the fact that for dealing with the unit circle, x squared plus y squared equals 1, this means the radius itself is equal to 1. So that means next, with a radius of 1 right here, I was able to say, go from the very center, and the distance from here to here is 1. Except that this is also the xy plane. So on the xy plane, we went left 1 unit to get to here.
Okay, so we're basically looking at it like it's on a grid. I see.
Exactly, yeah. It might be kind of helpful just to add the fact that this is the x-axis, this is the y-axis as well, just for emphasis there. And Christopher says, best way to get this is just memorize the basic cones from the unit circle, or the basic ones from the unit circle. Sorry, I misread that. Yeah, absolutely. That's kind of what these notes are all about. When we get to this part right here, this is where we get really good information on quadrant 1. And it turns out we can extrapolate all of that information into the entire unit circle going around this way. So I'm going to provide this information here on real exams in this format, tabular. It'll be our job to get familiar with where things fall on this grid right here so we can do the evaluations. Yeah, go ahead, Luke.
So you're always using a unit circle when you're using cosine and sine, correct?
Exactly, yeah. So that's one of the weird things about those definitions is the definitions of both cosine and sine themselves are fundamentally based off that one specific circle, where the center is at 0, 0 and radius 1.
Okay, so do you kind of, what if you're working with a circle that has a much larger radius? Would you then just assume a unit circle for calculating those functions, or how would you do it?
In that case, sine and cosine would be undefined on that circle. Sine and cosine are only defined on this specific unit circle. So if we had, say, a circle of radius 5, we couldn't do sine and cosine on that circle whatsoever. What we would have to do is divide the radius by 5 to bring it down to this one specific shape. So again, that's a weird thing about our trigonometry. It's based specifically on that one and only one algebraic structure. X squared plus y squared is 1, and no other circle whatsoever.
Okay, thank you.
Absolutely. Other questions so far? Thanks for these questions. These are all the exact questions you would want to ask for such a weird way to define a new function. Again, if you're in college algebra, you would define a function by saying, my function is named f. It takes for the input x and output x squared minus 3x, and then you're done. You have total information on everything that parabola is going to do. This is way, way different. Trigonometry is considered a much different kind of function than that one. In fact, if you try to put down a formula like this for cosine or sine, you can get something approximate, but you need infinitely many terms to add on. There's no finite way to write down a formula for either cosine or sine. Its most fundamental way of defining is through this fundamental object, the unit circle geometry itself. Again, that's kind of why it's a true credit course taken away from pre-calculus 1, ordinary college algebra material. Well, let's try this out again. This one feels a little bit different because it's a negative measurement. It says negative pi over 2, but we just have to recall if it's negative, that means we're rotating in the clockwise correct direction, going down here. So we would terminate in this location. This is negative pi over 2. Let me try again on that too. You might have also recalled, well, that's just a different way to say 3 pi over 2. And it's absolutely true. Sine at negative pi over 2 is identically equal to sine at 3 pi over 2. It's because it has the same second coordinate. So once again, all about specifically coordinates on the unit circle. Coordinate here at negative pi over 2, we go down 1. So that's going to be a negative 1 on the second coordinate. X coordinate on this one is 0. That's now we just take those coordinates and make the recollection. Sine itself is always the second coordinate, so it's negative 1. Really not sure why I put sine first on the right-hand column. It wasn't meant to trick us, but makes us think about it, so I guess it wasn't a bad call. Cosine at negative pi over 2 means go to that position, grab the first coordinate, and then we're done. Cosine at negative pi over 2 would come out as 0. Well, that's our warm-up example on these notes, just getting started doing these evaluations. But these are some of the key examples that come up loads. If you're imagining that you're taking, say, lots of calculus and you're in calculus 2, this stuff just shows up everywhere and you're just expected to simplify it. You're expected to recall your trigonometry and calculus courses, engineering courses, physics courses, and this is just us getting started. Well, the next part of the notes is going to be for our first big formula, the so-called Pythagorean identity. After we get the Pythagorean identity, we can do a pretty interesting example too on evaluating sine and cosine for an unknown angle where we already have one coordinate. But first, let's start with the Pythagorean identity itself. This is known as the key identity in trigonometry. And here's where it comes from. Let's take this as just a temporary screenshot. Take it down below here. So it says, for any angle t, and that's nice. It tells us the formula is going to work no matter what happens. That's why it's referred to as an identity, something that's always true. Sine squared plus cosine squared at that angle is automatically identically equal to 1. And here's the thought of why that must be true. All I did is copy the definition of the sine and cosine function. Let's call this a derivation. Sine. And by the way, that's the full way of writing out the sine function. That's just an abbreviation. And cosine. That's the full way to write out this one. Cos or cosine is the way we usually say it. And if you ever want to write out full, that's the full name. Sine and cosine are defined as follows. Cosine x, cosine at t is x, sine at t is y. But that means if you take this right here, x squared plus y squared equals 1, this is where x and y have come from originally, the ordinary unit circle itself, you're just making a substitution. If x is cosine at angle t, x squared is just cosine squared at angle t, plus if y is sine at angle t, y squared, written this way, is sine squared at angle t, equals 1. And then we're done. That's the original Pythagorean identity. Extremely rapid derivation. And one quick note, these exponents might look kind of strange in a way. There's different ways to write this out. You could say cosine at angle t squared is just saying cosine at angle t times cosine at angle t. And a very common shorthand in trigonometry is just to rewrite this all as cosine, putting the power 2, and then the input to the function t in this way. So we often write it out this way. That's why it's here on paper, just to get used to it. This is just ordinary exponential form of cosine squared. And that's an alternate way to write it if you so choose. Just know if you write it this way, the parentheses are now considered mandatory. Other words, you might have been confusing readers of saying cosine t squared, and that's a whole different thing altogether. Looks like we have like 2 seconds, so this is probably a good stopping point for us today. When we come back next Monday, we'll go through these notes in full and apply the Pythagorean identity to example 2 below. But any last questions, folks, before we call tonight? Okay, well, have a great evening, folks. It's weird to only work for 15 minutes and then we're already on the weekend again for as far as this course goes. But have a great weekend. I'll see you all next Monday.
We did get a question in the chat.
Oh, thanks for pointing that out. The first exam is going to cover sections 5.1, 5.2, and 5.3. I was thinking 5.4 originally, but I don't want to rush through the material. So 5.1 through 5.3 is going to be the definite coverage. And I'll make that more specific on the website over the weekend as well with some study problems. You bet. Sorry for missing that question.
All right, see ya.
So
Yep,
I
take
do have
care.
one question real quick.
Yeah, go ahead.
You are going to get in touch with all of us about how the exam is going to work this coming week or two, correct?
Yeah, I'll be contacting you individually. The Idaho Falls Testing Center, the Pocatello Testing Center, and the ones on various states all have slightly different procedures. So I'll be sending out emails to everyone individually to let you know just how all it goes.
Okay, cool. Thank you.
Yep, absolutely.
All right, look forward to hearing from you again. Take care.
You too. Have a good one.
Thanks. Good night.
Good night.